Our next speaker is Senya Shlosman. Is going to be talking about properties of the interfaces in multi-phase regimes.
Okay, thank you. So the interface is something which we see in the is something which we see in the multi-phase regimes, and their presence is a reason for slowing down of relaxation times, and so this is why they are important in simulations of Markov chains and studying of their relaxation properties. But they are also studied in statistical mechanics in their own right, and so I will talk about them more from statistical mechanical point of view. So the most known example of the interfaces and the properties comes from the Ising model. So the Ising model is a collection of random variables sitting on a lattice and taking values plus minus 1, and then you have the interaction function, the energy, which is given by a simple expression, sigma s sigma t. S and t are nearest neighbors, and then you consider the probability distribution, which is exponent of minus the inverse temperature times the energy, and you normalize it by the partition function. And then if the temperature is low enough, then we know that the Ising model undergoes phase transition, which means that it has two phases, so-called plus phase and minus phase. Okay, so plus phase is a phase where you see mostly plus spins, and minus phase is the opposite one. And then one is interested in knowing what would happen if you force the two phases to coexist in the same box. And you do this by taking a box and by freezing, say, half of the spins at the boundary to be minuses and the other half to be plus. No. And then the two parts of that box has to be separated in some way. So then we have this random object, and this is the interface that we're talking about. And the property of that interface depends on which dimension we are in. So in dimension g equals 2, what we will see is this picture. So then the interface would be just a line. And if the size of a box is n by n, then that line fluctuates quite a bit. So that strip where that line sits is of typical size of square root of n. While in case of dimension 3, well, the picture looks the same, except now it is three-dimensional. And again, we do the same thing. And now we have an interface. And then this interface is much more rigid than this line. Namely, well, it stays basically in a strip of constant width. So it's some constant here, depending on the temperature, which is beta minus 1. Well, constant means, and this constant does not depend on the size of the box. The precise meaning of that statement is that if you take some location, say at the origin, and then you give yourself some window, and then you ask what is the probability that your interface would go outside that window of the width, say 100 is a custom here to do. So then this probability is small, and moreover it goes to 0 as temperature goes to 0. So that that state, and this is the property which is called rigidity, and this rigidity was proven by Roland Dobrushin more than 30 years ago in 1972. And since then, that subject developed in a big chapter of statistical mechanics. So that kind of result was also established in other models, Potts model, and then also the shape of a crystal was studied using that kind of questions and answers. Okay, now in the Markov process community, some people like discrete time and some people like continuous time. And in statistical mechanics community, some people like discrete space and some people like continuous space. I mean here the spin space, the space where not the lattice for me would still always be there, but I would like to ask the same question in the situation where our spin variable is not a discrete variable but takes some values in some continuous space. And the simplest for me would be to talk about the case when sigma s now takes values. Before it was taking value in a zero-dimensional sphere, right? And now I take it to be one-dimensional sphere, so just a circle. So it's an angle on a circle, if you wish. And then again, my energy function I will take to be minus, again, sum over nearest neighbors. And here I will put a cosine of sigma s minus sigma t. So this is called XY model. And then again, I would like to know what are the different phases there and how to put them in coexistence and what the picture would be. And again, the situation depends on the dimension. So in three-dimensional case, what is known is that that model now has lots of different phases. So you go to low temperatures, then you take a box, and then you fix your boundary spins looking into the same direction. And what you would find out is that inside the system does remember that direction. So in the middle you would see some fluctuations, of course, but the expected direction of every spin being in the middle is roughly the same as you have on the boundary. So you have also many, well, here you have continuum different states which are parameterized by this direction. But this is in three-dimensional case. In two-dimensional case, that is not true. So in two-dimensional case, you don't have that kind of memory effect. Still, at low temperatures, what you would see is that if you take two neighboring sites and you look at what your arrows are doing, you will see that they are more or less parallel there. But if you go to some other location, you will see the same picture, except that they will also be almost parallel, except they will look in a different direction. So the memory of the direction that you might try to put on the boundary would not have an effect inside. Well, there are some other interesting phenomena in the two-dimensional case, namely that correlations at low temperatures in that model decays only as a power law, but the memory is not preserved in two-dimensional situation due to this continuous symmetry. Okay, so then we might try to play the same game as we were doing here. We can we take a box, and then we put, well, we take two boundary conditions. Say here we put we freeze all those spins looking in one direction, and here we do something we choose another direction in hope that in this way we will create two phases, and then they will exhibit some interface. But in fact, this is not what will happen. Due to the continuous nature of that system, it prefers, instead of forming an interface between those two phases, it prefers just to go continuously from one direction to the other direction. So you will not see any interface between those two phases in such a situation. And so for some time, it was a feeling that in continuous symmetry case, nothing like the interface can be seen. But in fact, this is not exactly the case. And so there are still situations where you can see such interface even in continuous space setting. But for that, you should further modify your interaction. Namely, what you should do, well, this is your minus cosine function. So you should do, well, something which looks innocuous. You just should deform it to something which looks like this. Okay, so you just squeeze it like this, and you just make this well here, well, much narrower than it was initially. And then you ask the same question. Well, and even before that, you also might ask what are the phases, different phases that you would see in that situation. And the answer is now the following, that unlike the XY model, which is up there, the phase diagram now is different in that situation. Namely, what one can show is that for every such this way looking interaction, one can find the critical temperature, at which temperature the following happens. You have two, well, maybe I should start from the other end here. So, so at high temperature, of course, system is highly chaotic, so it looks almost like a system of independent random variables. And at low temperature, you have the same kind of behavior. You have this local ordering or even global ordering in three-dimensional case. But now, if that minima here is narrow enough, you have a critical temperature at which those two regimes coexist. Which means that, well, you take a box, you take a square box, and you stay at that very critical temperature. And depending on what kind of boundary condition you put, you will see different pictures. So if you take chaotic boundary condition, then you will have some almost independently looking collection of arrows pointing in various directions. While if you take an ordered boundary condition, then at that same temperature, you would see some ordered state in the sense that either it will have this local order or even this global order. Okay, and this is something we have proven with Arnold van Enter a couple of years ago, and it is a right situation to ask about the interfaces, because this is the situation where they do happen. Namely, you should go to three-dimensional case, and then you will have a picture which looks pretty much like this one you see in the Ising model. Namely, morally, what our result means is that you put those two things together. You put the ordered boundary condition on this top size, and then you put chaotic on the bottom. And then what you would see would be an interface. which separates those two regimes. So here you will see this chaotic phase, and here you will see this ordered phase. Okay, and moreover, the result that one can show here is that this interface is again rigid. So like in the Ising model, like in this result by Dobrushin, this interface is undergoes very small fluctuations. They do not diverge with the size of the box.
It's only at this special temperature? Or?
Right. Because at other temperatures, those states just do not coexist. So this interface you can see only at the critical temperature where the two coexist.
So if you use two ordered boundary conditions, you get a smooth interface?
Right.
And what did you mean up there, even in the original XY model, when you say there's no interface? I mean,
Well, I meant some speculation. I'm not. You try to see whether you should expect the interface, and
what
see.
What do you mean by having an interface or not having an interface? I mean,
Well,
the spins have to go somehow.
That's correct,
from one
and
angle to
they are doing that in a continuous way. That's what you make computation, and this is what you see. So they just vary continuously from that value here to this other value there. Okay, you might wonder how they will do that if you do them just opposite, and the answer is somewhat interesting, but still they don't form interface in no way in any sense.
What does that mean? That the width of the region that you need to go from one to the other grows with n?
That's correct. Yes. It's of the size of the whole system, so to say. Yes. So yeah, just the magnetization just continuously go from that value up to this one once you move in your box.
Okay, why do you see the interface only at the critical?
Well, see, because the interface is between what and what here in my setting. It is between the chaotic phase and the ordered phase. And there is only one temperature at which both exist. So at other temperatures, either one is not present or the other is not present. And that's why there is only one temperature at which you can hope to see the interface.
But what if you, at low temperature, put the same boundary conditions as you wrote there? What will the picture
This will be the picture.
No, if you put half chaotic and half ordered
Right.
at low temperature.
Then what would happen is that yes. So what would happen at low temperature if I do this, right? This is what will happen, so to say. So the guy who is more important would use just the whole space and will push everything to the boundary. So just that phase would win over because this is just a peanut then.
Once you draw it.
Yes.
Is another way of what you're saying that the surface tension between two ordered phases is zero, but the surface tension between ordered and disordered
This is I would say we are not using that. We don't talk about surface tension, but that's how things are. Yes.
And if you have the whole boundary disordered at low temperature, then you'd expect it to just choose an ordered phase.
Then if you take all your boundary disordered, then in the middle you would see mixture of ordered phases.
Yeah.
So it would be one or the other one, or well, you will see all of them, and each one with zero probability, so to say, because there are infinitely many of those. So it will be a mixture. It will be the mixture state. Yes. Well, okay. Should be. That's delicate how you prepare that mixture. The weight at which different phases are entering then depend on exactly in which way the mixture outside is prepared. but it will be the mixture and the way the different phases are mixed in that mixture, that depends on the boundary, on the choice of your boundary. Okay, well, more exactly speaking, well, what I'm talking about now is a paper we did with my student Yvonne Vigneault, and which was published last year by Communication Mathematical Physics. Well, what I just told you here is if we talk about, if you go down to the level of theorems, this is not exactly precisely what we were able to prove. The precise statement in that setting, unfortunately, is a little bit weaker, and it is the following. So imagine we're talking about such an interaction, and this well has the width of epsilon. Then this picture indeed holds, but unfortunately, you cannot go to the full thermodynamic limit, to the limit of when all the three dimensions of your box go to infinity. You have to stay in the in the slab of some width, L of epsilon. And if you want to go to wider one, you should make your epsilon smaller. So this statement we were unable to establish in its full natural generality, but there is a model which I am going to tell you about now, for which you can do things completely, but then we go back to the discrete spin setting, and it is the following modification of what I was just talking about. So now we will still take our spin variables to sit on a circle, but actually not a circle, but we just take a big discrete group in a circle. So we take what is called clock model. So we allow only discrete subset of a circle, equally spaced. And for the interaction in the model, one should take something which looks like this. So this will be, again, the interaction sigma s, sigma t would be a function which just depends on a difference. So it has still symmetry, which now will be Zn symmetry. So this is, and that will be the graph of my function u. So it looks like this one, but the simplest case you can think about is such a graph. Okay, so you have here you have width. You just have maybe, I don't know, say 5 positions allowed here, and then n is a large parameter. So you're talking about a discrete system, and at low temperature the situation looks like that neighboring guys, they are not exactly the same. They can differ, but at most some finite number of neighbors. So if that one was k, the next one can be k plus 2, k plus 3, but not much further. So we have still infinitely many configurations which are ground state configurations. And
the energy of the bad things is not plus infinity.
No. The energy of the bad thing is another constant. Yeah. Yes. And the energy of the good thing is, well, some different constant. So the simplest would be just to have 2 constants here. And in that situation, everything I told you is really correct in a true thermodynamic limit. So that at low temperatures you have locally ordered states, so to say, and at high temperature, of course, you have this chaotic situation where you have almost independent situation, and then there is again a critical temperature where chaotic phase and ordered phases, whatever that means in that context, coexist. And moreover, the interface between those two again is rigid random surface, which undergoes fluctuations which are just finite and do not diverge when the size of the box goes to infinity. And
But in this case, surely the ordered phases at low temperature also have a non-zero surface tension, but maybe one that's something like 1 over n.
See, here my function is identically constant. So I doubt that this is the case.
I mean, it's certainly true if there's one allowed state, then you have the pot.
Or that's correct, but
with
that's,
the
so what I insist on is that Potts is studied before, and the crucial difference between that situation and the Potts is that at low temperatures you have power law decay of correlations. So I'm not sure that the surface tension there. I don't know what to say. I wouldn't know what to say. And in two-dimensional case, you don't have many states, many low temperature states. Just one. My feeling is. Okay.
That's not proven because
No.
we don't yet have a Riemann-Wagner theorem for these kinds of things.
Yeah. This is discrete situation, so it is not.
Even if it were continuous, because
In the continuous situation, then, well, in the continuous situation, it is, say, but for the xy two-dimensional with no due correlation inequality, that the state is unique at every temperature. And to conclude, I just want to say 2 words about how that result was proven. And the method that we are using is called reflection positivity. And the key corollary of that method is the following correlation inequality. And I want to put it on the blackboard because it looks nice, it seems to me. So in the situation where you have this reflection positivity property, imagine you need to estimate an event that in some box you see some event which I would denote by a letter B. So you want to estimate that probability from above. And in the setting where reflection positivity holds, you have the following bound. What you should do, you should take your box, and then you should repeat it again. And you have to put that same event here. And you put a reflected event there. Okay? And then you put 1/2 here. And then you can iterate this. Now you can guess what I'm going to draw here. So you have this event, then the reflected one, then you reflect it again, and then you reflect it once more. Okay, and then you put 1/4 here. And okay, and then you go on and you have more and more events, and what you see is easier and easier to estimate. But the proviso here is that you really have enough symmetry in your setting, right? The most symmetric setting would be a torus. If you're working on a torus, that means that you're talking about periodic boundary conditions. Then you have as many symmetry as you can wish to have, and really you can repeat those things. And then you can cover by your local event the whole box, and then to estimate the probability of that is extremely easy thing to do. Well, this is not quite what one can use here, because see, we want to enforce the interface in our box. And if you have periodic boundary conditions, interface would not come there. You would just see all pure phases. So what the compromise was to take a cylindric geometry. So you take a cylinder, which is a two-dimensional torus times the segment. And then you do your reflections only in horizontal, only in vertical planes. And okay, this is less than you might want, but it's enough to do the job for us. And then you put some bound, say you put ordered here, and you put chaotic here, and then you force the interface, and then you study that situation, and this is how you get your result. Thank you for your attention.
What kind of dependence on epsilon you have for L of epsilon?
Well, I would not be able to tell you exactly, but this is a technical thing, so anyway, it's of no so it has no meaning because it should not be there. Except, well, see, that method of reflection positivity, unfortunately, is not something which gives you full control of the situation. You have what you get. You should be satisfied with what you have. and unfortunately, in that setting, it doesn't allow us to quite take the full thermodynamic limit, but this is just the shortcoming of the method. It doesn't have any truth in that.
It might be a naive question. What's the meaning of continuous spins? The physical meaning? I mean,
Well,
I can spin one plus or minus one, but
but if once you're doing field theory, this is what you have to consider. So your fields then are taking continuous values, and so this is a natural setting from physical point of view.
Well, many physical, in fact, probably most physical ferromagnets like iron are, you have a little atomic spin, which can actually point in any direction on a sphere, and you have complete isotropy.
okay.
So in fact, it's this model with S2 rather than S1. So it's actually only a small number of ferromagnets that for some reason, because of the crystal structure, they're uniaxial and tend to point up or down.
Thank you very much.
I thought the question was going into direction of quantum mechanics.
Oh.
No.
No. Okay. So, and then it was.
Well, thank you for speaker again.
Hi.